will be free from today evening, and Saturday will definitely be there. So that is,
Oh,
we are facing the same problem. All our faculties are engaged in the examinations. Is a problem. But other universities not an issue. Only for Anna University this is a problem today.
okay, okay. Today is a very peculiar and research topic.
Yeah, yesterday itself I gave a intro about that. Like by the end of the session yesterday, I informed the audience about the topic which you are going to discuss today in the two sessions. So I said them, please don't miss it. Like it is something very different. The deep learning in terms of using reliability concepts, a decision support system in payment management system. I said yesterday itself. I said
Okay.
so. I think hope people will join and get benefit. You will see. Good luck to all.
Good morning, Arnav.
Uh, Shobana, you can start introducing about sir because sir has a conference to be attended at 11:30. So, start.
Okay, sir. So good morning to everyone present here for the day 5 of SCTP program of phase 2. So without further delay, let us start the session. I welcome Dr. SAKTHIVELAN Ramachandran sir, who is a civil engineering graduate from AMIE from the Institution of Engineers, Kolkata. He has postgraduated in structural engineering at IIT Madras and received his PhD from IIT Madras. He has additionally an MBA from a Madras University. Research areas include bridges, curved structures, finite element analysis, vibration-based damage detection, new and old concrete interaction, pavement evaluation, PMS, BMS, optimization, uncertainty, risk and reliability, Markov process, fuzzy system, ANN, simulation, system dynamics, and ML or DL in infrastructure engineering. He has 30 years plus industrial, teaching and research experience. Presently, he is the director, that is operation for RAM Engineering Consultancy Services, primarily on design of bridges and highways. It is designed and audited more than 250 bridges and the highway section. Because of his academic passion, he has provided a number of technical lecture, conference, training courses, and FDP or STTP to the academic institutions like us. He has guided more than 200 DTech and ME or MTech project students as external guide. I welcome you, sir. I'll just hand over the session to you to deliver your lecture on the reliability concepts in payment design.
Sir, you are inaudible.
Sir, you have unmuted your mic, sir. Sorry, you have muted your mic, sir. You can unmute and you can talk, sir.
Is my screen visible?
So first it is visible, sir, before 2 seconds. Now it is not visible, sir. Yes, sir, now it is visible, sir.
Okay, fine.
It's visible, sir. Go to presentation mode.
Yeah, I'm trying to get it. Now it must be in the presentation mode. Is it okay?
Yeah, it's your to
Yes, sir, fine.
clear that, hide that once a small thing is coming, stop sharing, hide. You have to close it. Yeah, that's fine.
Okay, fine. Good morning, everyone. This is SAKTHIVELAN. Actually, this is the topic on the reliability concepts in the pavement design. Actually, we can split it into two parts. The one is the reliability itself, a separate concept. As you know pretty well, by this time, those who have attended the previous session are from the current FDP course, you might have undergone the pavement design also. So how it has been incorporated, how the reliability has been incorporated in the pavement design, just we are going to discuss. And we will see what is the reliability first. Is it not so? Okay, see, this is what you call it, it's a type of advanced topic, but it is not. The topic is only advanced, but the concepts are not so advanced. Okay, so all these concepts are only the fundamentals, and we are trying to adopt these concepts into the system. That's all. Okay, and those who know about this, much know about this, you can also discuss to your friends at present. And those who do not know about this, we can discuss. Yeah, you can just discuss to me, or at the end of the session, or even after that, you can mail to me. And those who want to take up research on these areas, you will discuss. No doubt on it. And now we will see how the concept can be explained. Reliability is nothing but the what you call it, the opposite of the probability of failure, or the inverse of the probability of the failure. That is, the inverse is the sum of the reliability and the probability. Both probability of the failure is summed to be 1. That force, they are complementary to each other. Therefore, the probability that the pavement expected to fail, or the probability that the system expected to fail, is called as probability of the failure. On the other way, the reliability can be said as the probability that the pavement is expected to survive, or to have an intended intended service life that can be performed over the planning horizon. Therefore, that can be said as RP equal to 1 minus FP, that is 1 minus failure probability. Therefore, for example, a failure probability is 5% or 0.05. The probability of success, or otherwise the reliability, how it can be reliable, can be set as a 95%. It means the 5% of the system can go wrong. That is the maximum 5% of the system can go wrong. So in which see, the entire system have more number of components. Therefore, each component will have a separate reliability. Therefore, you have to find out what is the reliability of the each component. Then you have to sum it up. Okay, sum it up means it is not a algebraic sum. So here, how it is summed up, we can just see. So how it is connected to each other, how it is integrated to each other, it matters. Therefore, how each component is integrated, that is what it means. Therefore, if each component fails, that is the system fails, if any one of the component fails. So we have a different components. Even if one component fails, the system fails. It means the system is connected to series of components. Okay, it's a series of components. For example, in an extraction of a hydroelectric power, we have turbines and we have water storage. So when this turbine S1 and water storage subsystem, 2 subsystems are there. These 2 subsystems are connected seriously, because even if the turbine is gone, failed, or if there is no water storage, you can't get the power. So therefore, you can see that on the right hand side, see, there is a switch here connected in series. You have switch A and switch B. That can be said as what do you call it? It is analogous to that of the systems in the series. A and B are connected in series. See, if both are logged, that both are switched on, then only the light will be on. Therefore, this is analogous to that. Therefore, both are required so that this system is pausing. Therefore, if anyone gets failed, the system gets failed. That is the analogous. For example, you have a road construction. You have 3 types of systems. Therefore, which maintains temperature, binder content. Another one is gradation. For example, if anything goes wrong, the road construction cannot be carried out. Therefore, all things are required. Therefore, the road the road material should pass through temperature, should pass through binder content, should pass through gradation. That is what the mixture should get passed through all these 3. Therefore, the reliability gets connected in the component reliability gets connected in the series. For example, in another example, I am telling you, in case of bridges, the bridges have different components. So you have 2 abutments. Abutments are nothing but the end supports, and we have piers up to N, P1 to Pn. Therefore, the piers are nothing but intermediate supports, and you have deck. Okay, deck from D1 to Dn plus 1. Okay, therefore Dn plus 1, that is N plus 1 decks will be there if N piers are there. Okay, that is what I put. Therefore, this much components are there. Okay, these components are connected in series because the bridge as a system will function if anything fails on these components will get failed. Okay, therefore the system in the bridge is also a series system. Many often in the world, all the systems are in the series. For example, we know R1 and F1 are the reliability of the failure of a component 1. Therefore, R1 can be said as 1 minus F1. Similarly, R2 and F2, we can say that R2 is equal to 1 minus F2. Therefore, if you want to find the reliability of the system, okay, it is nothing but the product reliability of the component. For example, this is equal to that of your probability concept, or you can say, okay, it is equal to that of your probability concept. Therefore, RS equal to R1 into R2, because reliability is nothing but it's the probability of the success. We can say favorable condition. Therefore, RS is equal to what? RS means the reliability of the system can be expressed as the product of R1 and R2. In general, if you have a multiple system, multiple subsystems, R1 to Rn, therefore the reliability is nothing but the sum of the products of the reliabilities. You will see reliability of system. The reliability will be more than the. I'm just telling about some corollaries of the series system. Okay, the reliability will be more than the minimum. Sorry, it is less than. Reliability is less than the. Reliability will be less than the minimum component of the reliability. For example, see, R1 is 0.9 and R2 is 0.8. Therefore, the R1 is nothing but the component reliability is 0.9 and 0.8. R is the system reliability. So R is nothing but 0.9 into 0.8 will be 0.72. See, this 0.72 is minimum of R1 and R2. Minimum of R1 R2 is 0.8. Therefore, you can see the combined reliability or the system reliability will be lesser than that of the minimum reliability of the individual components. Minimum reliability of the individual components. Therefore, we should be very, very careful in selecting the reliability of the each component. Therefore, if you have a minimum reliability, therefore, of the component, your system reliability will get reduced in that. Okay, see, for example, if you have a number of systems of same reliability, okay, number of systems of same reliability. For example, 0.96 is highest. 0.96, you see how highest it is. 0.96 is the reliability of the individual system. Okay, it will get reversed. It means the reliability gets 0.04. That is 0.96, 1 minus 0.96. That is 0.04. Therefore, the reliability can get reversed when you attach 79 components. Okay, when you have a 79 components, what happens? You see, is all 96% reliability gets reduced to only 4%. See how bad it is. Similarly, you can find a 97% reliability. Okay, it will get reversed in 115 components. So if you put a series of 115 components, your 97% reliability of individual component will get to 0.03. Similarly, see highest one 0.99. So if you attach 458 number of components, it will get 0.01. Therefore, you see, this can say you can understand that even though it has a higher reliability, if you get it in a series of that, it gets reduced. Therefore, you can think about in the natural phenomena also. You can have more number of good peoples when they are advised to get information from them. See how reliability get reduced. Therefore, you should see it should not be in a series form. That is what. Okay, it should be in the another way. That is what I would like to say. The second one is reliability of a parallel system. See, in a parallel system, you see here I have shown on right side. Here I have shown on the right side there is a lamp and you have two switches, S1 and S2. Okay. See here what happens, even S1 is on, the light gets switched on, and S2 is on, then also light gets it's on. Therefore, what does it mean? Therefore, the system fails only if all the components are failed. That means S1 also gets failed, S2 also gets failed. Therefore, if S1 is switched off and also S2 gets switched off, then only lamp is switched off. Therefore, it means that this is called as parallel system. So, for example, what is an example for a parallel system? See, a dual power calculator. Dual power. You have a calculator, you must be knowing that it will have some battery power, also some photoelectric power. You might have seen that. Some solar power, solar power induced calculators. In which, so you can see that if battery power fails, the photoelectric power will get. Even in the night condition, your battery power will switch on and it will get powered on. Okay, that is it. That means the reliability is, so you can see the calculator is more reliable with respect to the power. So what we can identify here, so the system get more reliable. The reliability get enhanced when the system is on the parallel system. Okay, So, for example, you have a multiple engines in the aeroplanes. You might be knowing E1, E2, or these engines are connected in parallels because what happens? See, if one engine gets one of the engine is failed, the other engine will get ignited and the system will go on. Therefore, aeroplane will not get into crashes. Similarly, multi-cylinder engines. You have multi-cylinder engines. Okay, these are will have more number of pistons and cylinders. So that type of cylinder engines will have more power. But if one of these cylinder or piston gets damaged, then also the engine will work. Of course, there is a loss of power. Is it not so? That is it. Therefore, this is the advantage of the parallel system. But in natural cases, it will be having both parallel as well as series systems. Why parallel is there? Because these series systems will reduce the reliability. Therefore, to enhance the reliability, we will try to put parallel system. That is what I would like to say. Okay. Therefore, with the parallel systems in the parallel components are engaged in the system to enhance the reliability of the system. So we'll see with an example. R1 F1, therefore same thing, F1 is equal to 1 minus R1 and F2 is 1 minus R2, where R1 and R2 are the reliabilities, whereas F1 and F2 are the failure probabilities of the subsystem or the components. Therefore, now you see the failure is nothing but the product of the failure probabilities. Therefore, failure probability of the system Fs is Fs equal to F1 into F2. Therefore, you know Rs is 1 minus Fs on the reverse. Therefore, R equal to 1 minus R1 into 1 minus R2. Therefore, this is nothing but 1 minus Fs. Fs is F1 and F2. Therefore, I resubstitute. I get R equal to 1 minus R1 into 1 minus R2. Therefore, this is the reliability. Therefore, you can see like this. So, in general, we can say 1 minus R1, 1 minus R2, 1 minus R3, like that. Okay. Therefore, that is the reliability. Therefore, we can be reliability said as 1 minus R1, 1 minus R2, 1 minus R2, and so on. See now, for example, reliability of the failure is reliability will be in the parallel system. What happens? The reliability will be more than that of the maximum of a component reliability, more than that of the maximum of the component reliability. Whereas in the series, it will be less than that of the minimum component reliability. Here, the reliability of the system will be more than that of the maximum of the component reliability. For example, you have two reliabilities as 0.9 and 0.8. Okay, these are the subsystem reliability as 0.9 and 0.8. Therefore, what is the failure probability for the component one? It is 1 minus 0.9, that is 0.1. Similarly, for second one, it is 0.2. Therefore, 0.1 and 0.2. Therefore, 0.1 is 0.2 is nothing but your failure probability. Therefore, combined failure probability of the system is 0.1 and 0.2. Therefore, reliability is equal to 1 minus combined probability of the failure. That will be equal to 0.98. You can see that this 0.98 is greater than that of, okay, it is wrong here. It is greater than that of 0.9 or 0.8. That is what I would say. It is 0.9 is greater than that of 0.9 and 0.8. It is wrongly stated here. Okay. See what happens here. We want to have a combined reliability of 0.97. For example, we need to have a combined reliability of 0.97. But we have a reliability of 0.83 only. Component reliability is 0.83. We have several components having 0.83. So therefore, you add two components in parallel. You have two components in parallel. If it's 0.83, you can get 0.97. Okay, it's a combined probability. It's a combined reliability. Similarly, if you have a lesser reliability, 0.7, don't worry. Then you add 3 components in parallel. You have still lesser. You add 4 components in parallel. You have still lesser. You have 5 components in parallel. See, that is what. See, you have. It all depends upon you want to have 2 components or 3 components or 4 components or 5 components. All can be done to 0.97. But depending upon 0.83 or 0.7 or 0.6 or 0.5, the cost will vary, sir. Is it not? So if it is 0.83, the cost will be more. 0.7, the comparatively cost will be less. 0.6 means still less, and 0.5 will be the least among all these. Okay, therefore, accordingly, you can add 2 components or 3 components or 4 components or 5 components. And if you want to minimize the cost, you can make an optimization. You can see that there is a chance of optimization here. See, for example, the system, what I was telling previously, the reliability of the system. But what happens, reliability is a 1-point estimate. For example, it means it will tell the reliability of a system as a whole. Okay, but what happens, the reliability for a deteriorating system, many of the systems are deteriorating from the day one. Okay, from the human system, it also set to the human body also. Therefore, they all are deteriorating system. These deteriorating system, the reliability also reduces. See, even for one component, it is only one component. See, the deteriorating system, even if it is a reliability is 1, what happens? So it keep on reducing over a period of time. Okay, over a period of time, it keeps on reducing. This is the time scale. Okay, and it is what you call T by T naught is nothing but it is something is what you call it is normalized to some T naught. Therefore, reliability gets reduced, keep on reducing. So if it is 2 system, okay, so if 2 system is there. See, if it is connected in series. Now it happened. What happens? The reliability gets reduced and also deteriorating. Okay, it gets reduced and also deteriorating. Okay, if it is 3, then also like this. So it gets reduced further. If it is 4, it is still reduced. If it is 30, 10, 30, see how fast it reduces. Therefore, in series system, it gets very fast deteriorating. Therefore, not only, see, the system is not only in series will have a low reliability, but also the deterioration rate of the reliability is also very fast. Okay, therefore, this is what. Therefore, what I'm saying is R as a function of T. Therefore, R we can say as a constant reliability, but in a deteriorating system, R is a is a dynamic in nature. Therefore, R varies over the time. R varies in some. Usually, R deteriorates. Okay, R gets reduced over time. Okay, then see if it is in a parallel system, for example. If it is a parallel system, for example, if it is only one, it deteriorates like this. Okay, it deteriorates like this. See bottom one. Okay. If you connect it in parallel, then also you see get deteriorated only. Okay, but in a better way. Therefore, if you go for 3, it will deteriorate in a slower rate. Therefore, what I would like to say is the rate of deterioration can also be reduced. Therefore, systems deterioration, okay, the system deterioration can also be found out. Therefore, the reliability of the system deterioration can be enhanced. If you go for a parallel system. If it is in a series system, it will be like this. But what I was telling you, okay, the system is always a series system. Okay, because all these are connected in series many often. Okay, so when it is naturally connected in parallel, we will discuss later. Okay, it is only hidden. We do not know. This hidden is called as redundancy. Okay, that redundancy. Okay, that we will see in the later time. For example, see, you have a 5. You can compare this n equal to 5 and n equal to 1 here. For example, okay. See what happens. N equal to 5 systems are there connected in series. You just put it here in the parallel system. Then you add similar n5 system in parallel. You can enhance the strength. Similar 3 such systems. Okay, you can enhance the reliability. Therefore, that finally you can try to bring it equal to n equal to 1 here and n equal to 3 here. You can compare here. Okay, so therefore you have to see the system is available. The system exists as a series system, and what you will try to put a parallel components to enhance the reliability. Therefore, while doing some parallel component, you have to invest some amount. Okay, therefore that is the cost you have to invest. There are the reliabilities intrinsically hidden. Those reliabilities are got from redundancies. So this is what I would like to say. Therefore, to have a lower reliability, the initial cost will be less. To enhance the reliability, what happens? The initial cost will be more. See, For example, what I was saying, you see, you want to have multiple engines. Okay, you have to have a multiple engines connected in parallel. You know pretty well that the cost will increase. But what happens? The post implementation cost, the post implementation cost will get reduced. You will not worry about the its performance. Therefore, this will take care of the performance because you have invested more on the 3 machines. Therefore, what happens? See, post implementation cost reduced. Therefore, we have to compare, add both the cost. See, the total cost will be this, and it will keep on reducing up to particular reliability. Then afterwards, it will get increased. Therefore, you can find what is the optimum reliability that will give you a minimum cost. Okay. Therefore, this is also a research topic. Therefore, here what I made is minimum cost concept to have a optimum reliability, and there are chances you can enhance the reliability and keep the cost as a constraint. You can keep the cost as a constraint. For example, you can have a cost constraint level, maybe this level. Okay, therefore reliability can be this much. This much will be the reliability. Okay, therefore this is a typical system optimization on the reliability. Now we shall see. So therefore, how this can be applied here? Now, as you know pretty well, how the probability of failure occurs, because the failure occurs due to various reasons. Okay, various reasons of the load as well as the strength. Okay, load may vary over a period of time because the load is uncertain. This is the load we cannot predict. Okay, in a stochastic system, because many of the systems is a stochastic system. So we have designed those stochastic systems as a deterministic form. Okay, down and we might have introduced a little reliability concept into it. Okay, that's all. So therefore, what I am trying to put is what we will be doing a uncertainty design, that is reliability design, or you can say as the probabilistic way of designing things. So therefore, you know, strength is a parameter where is the distribution. For example, I have given here 2 distributions here. You can say that they are normally distributed. As you know how the normal distribution is there. So this is a normal distribution. Similarly, you have a strength distribution. Strength is here. See, for example, this load distribution and strength distribution are kept for. Okay, this is for here. It means this is the mean value. This is the mean value, and there is no interaction here. When you kept it for, it means okay, the probability of failure is very less. Okay, the probability of failure will be very less. Therefore, but if the strength is, for example, if it is large, for example, if I will say, for example, if the strength is M40, okay, if the load is only 2 Newton per millimeter square, okay, 2 Newton per, if the strength is M40, it is, for example, if M40 is 40 Newton per millimeter square. So what happens? The strength is far higher than the load. It means it may be safe. Okay, it may be safe. What happens? The cost will be more. Therefore, what you do, you try to get closer. Therefore, if you have a strength is 40 Newton per meter square, you have to design for a load of less than 40 Newton per, closely less than, maybe 40 Newton per millimeter square. But you see, there is a large variation because mean only 40 Newton per meter square. Okay, and there is a chance of 45, 50, 55, 60, 65, like that. Similarly, 35, 30, and 10. Therefore, this is the variation of the load. Similarly, the strength also may vary. Okay, because of the various reasons. Because of the, for example, the quality of the sand may be bad, the quality of the aggregate may be different. Okay, the construction practice, there are many reasons for those cement properties. Even though you accommodate in the quality control, okay, in the quality control, what you say is you provide a range. Okay, if that range is fine, you are saying it is fine. Okay, even if that range, the strength is varying. Okay, as I was telling you that each component is each is individually is given a range. Therefore, when they are connected in series, you see what is the probability of the success as a whole. Okay, you know that from the reliability concept. Okay, therefore, when you agglomerate things, the probability gets multiplied. Therefore, failability probability or success probabilities also get multiplied. Therefore, the overall strength gets reduced. That is what I. Therefore, in the strength parameter, so there is a variation from lower level to higher level. But what we find out is M40 as a mean strength. Okay, don't worry about the what you call M40 as a design concept. What we will find out later. Okay, what definition of a M40 or M30? Okay, how reliability is fit in. Similarly, load. So load is like this. So what happens to these here in this diagram? See, they lower tiles. Okay, they merge to each other. It means there is a probability that they interact each other. It means load is, there is a chance that load is lesser than that of, greater than that of the strength. Therefore, that chance is called as failure probability. Therefore, if you keep this black and red two apart, this will be safe. It means the margin of safety is more. So what you do is you keep closer and closer such that the margin of safety is less, and you also identify there is a chance of failure, and you accept there is a chance of failure, because you can accept because you cannot make the things always good. Okay, you have to accept the failure. You have to accept the probability of the failure. Okay, if there is a probability of failure very less, you can accept it, still accept it. Okay, it all depends because the engineering goes like that. You have to accept a little probability, because if that comes, we will take care of it. Okay, but we cannot. In other words, I can put it there that way. See, for example, if I would like to redesign, if the failure comes, say 100 rupees. Okay, so if I make a good component that does not fail. Okay, if it is say 600 rupees, why should I invest 600 rupees to that for a which is not failing? Okay, rather you invest 100 rupees. If the circumstance comes, let it fail. What is that? You redo it. Okay, but whenever the threat is come for life, therefore in such cases you have to go for a enhancing the reliability. That way you have to adopt the whatever, parallel system. Okay, that way that is an extra engine you have provided in the aeroplane, like that. Okay, so therefore whenever the what you call how the risk comes, that matters. We will discuss how risk affects the reliability. That's also fine. So previously, traditionally how the things were made. So previously what we did is a factor of safety only. So you have a factor of safety like this. See, only a single point, that is mean here, mean here, mean of strength, mean of load. Therefore, mean of strength and mean of load is having a mean of strength divided by mean of load is equal to say 5 times. It means we have a 5 times factor of safety. That is a traditional approach. 5 times that is 2 means are compared. That's all. That is it. Thing that you can think about in the working stress method. Okay, you have a factor of safety there. In the later stage, we are trying to reduce the concept of that is the margin, safety margin. Then how the safety margins can be reduced? See, for example, what we do is here you have a load. Okay, you enhance the load. Okay, you enhance the load. You have put some partial safety. You can enhance the load, what we call as load factor. Okay, you multiply the load and have an enhanced load. Similarly, you have the stress resistance. Okay, you make some partial safety factors and they call as a knockdown factor. Okay, partial safety factor, and reduce it. See what happens now, the margin get reduced. Therefore, you can get the economy. This is what we have found out from your limit state approach. Okay, this is what we have found out from the limit state approach. But there is still possible to have a probabilistic approach. Okay, in a probabilistic approach, there is no doubt you should have a particular how load varies over the or how load gets distributed. Okay, so how load, that is maximum, that is mean load and maximum load, minimum load, how it gets varied. Okay, therefore this is a mean load. Mean load is here. Similarly, resistance. This is the mean resistance and maximum and minimum. See here the distribution is widespread. Here the distribution is narrow spread. That you must know. Okay, how distribution gets this. Here the distribution is flat. Here the distribution is narrow. Okay, how the distribution moves. See in both cases these are normal. Okay, normally distributed. Here the distribution is how it is little flatter. Here little steeper. Okay, if it is normally distributed, it is called as meso. Okay, mesokartic. If it is steep like this, it is called as what again? Leptokartic. Okay, there is still flat is there. You can see that is called as platykartic. Therefore, this is nothing but the kurtosis point of view. Okay, here similarly, how loads are distributed and resistance are distributed, both are distributed merely normal distribution. So normal is like a bell distribution. Okay, it is symmetrical to with mean. Sometimes it will be skewed left. It will maybe like this, skewed left or skewed right. Okay, skewed left or skewed right. It may be normal or skewed left. For example, in a class, the students which are studying very good, those who get more marks, about more than 75 in a class. Okay, in such cases, it is skewed on the right side. You can see the average will be 90, minimum will be 75, maximum will be 100. Therefore, okay, so it will be like that. In a poor class, sometimes the people will get less than 50 marks. So in such cases, you see it is skewed left, in which the average will be 30 or 35, and the marks will be 0 to 10, or maximum mark will be 51, 52 like that. In such cases, it is skewed at the left side. Okay, many often in a system, in a normal system, it is normally distributed. That is what is said as a normal distribution. Now people will get a normally distributed over a range. They will not get more marks, they will not get lesser marks also. Okay, the average people will be more in the middle. That's all. That's what. This is what. Such way the load can be distributed. So the load distribution either can be normally distributed or mesokartic or leptokartic. Similarly, left skewed or right skewed. Okay, in what way it may have. Okay, so in any cases, all this will have a mean value and another measure is called as variance or a standard deviation. Similarly, resistances. Okay, resistance will have, okay, it may be distributed normally or leptokartic or mesokartic. Okay, similarly, left skewed or right skewed. Okay, in all these cases, it will have a mean value and will have a variance or a standard deviation. You know the relation between the variance and the standard deviation. Huh? Okay, fine. So here also you can see there is a overlap. Okay, whenever you find a overlap, it means there is a failure region. If the overlap is less, the probability of failure is less. If the overlap is more, the probability of failure is more. Okay, and the margin is less. Safety margin is less. Okay, right. You have see, I have given a simple example: load and strength distribution. Okay, in a normally distributed samples, normally distributed scenario. You have strength. Your strength as 500. Therefore, your mean strength is 5000 Newton per millimeter square. Assume that your mean strength, mu strength is 5000 Newton per millimeter. Therefore, mu load is 3500 Newton per millimeter square. So directly we will say in a what you call in a deterministic approach, 5000 is greater than 3500. It is safe. That is what we will say. Okay. That, but what happens in a probabilistic nature? What we'll do, we will find out what is the standard deviations also. Okay. For example, the strength is 5000 with a standard deviation of 500 Newton per millimeter square. Okay. With a standard deviation of 500. Similarly, the load is 3500 with a standard deviation of 400 Newton per millimeter square. Okay. In such cases, you have to find out the combined system standard deviation. As you know pretty well, the system variance is nothing but sum of the variance, okay, in the series. Therefore, as you have this, you might be knowing the probably those who have studied in the PERT and CPM. Okay, what is the in the PERT? What is the variance of the system? The variance of the system is nothing but the sum of the variances of the components, okay, activities along the critical path. Okay, same thing. Here both are critical. Strength is critical, stress is critical. Therefore, I found out these variances sigma s square and sigma l square, and see find out the variances, sum of the variances. Therefore, the standard deviation is nothing but root of variance. Therefore, combined is nothing but root of the variance of the system. That is what I put here as root of 500 square plus 400 square. It is 640.3. Okay, therefore, you substitute this in your normal distribution formula. This Z is a normal variate. Okay, here, therefore, therefore mu strength minus mu by sigma. This is nothing but a standard error, you can say. Therefore, in a probabilistic manner. So you find out 1500 by 640.34. It is nothing but 2.34. Therefore, in a normal distribution, you find out what is 2.34 corresponding to is 0.9904. Okay, 0.9904. It means the failure probability is 0.0096. Okay, the failure probability is 0.0096. Okay, you can use your Excel sheet and you can find out easily. Okay, 0.9904 and you'll get this. Therefore, what is the reliability of this? This is 99.04. Therefore, we have a higher reliability in this system. Therefore, see, not only here you can find out how the reliability varies 5000 minus 8. So, in the deterministic approach, we will think about only 5000 and 3500. Imagine that if you have a variance is more, okay, if you have a variance is more, so if the variance is more, the 640 will be more. You will have this is in the denominator, therefore Z will get reduced. For a reduced Z, you can have a higher probability level and reduced reliability. You understand? You will have a reduced, even though means are same. Okay, that is what I would like to say. Now come to the payment part of it. Okay, see here how your payment performance or your payment depends upon the different factors: environment, structure, construction, traffic, and of course the maintenance. So in a design concept as well, the variability exists from the traffic loading and the environmental factors. What is the environmental factors? How the temperature varies, the water ingression, rainfall, all those things. Okay, that is put it in a different form: ingress of water, oxidation of the binder, and to that extent there is a loss of volatile. And of course the design itself, construction practices. Okay, how you make the construction, construction practice, how you modern types of construction practice will have enhanced the reduce the variabilities. Payment composition itself, how the payment composition made. Drainage, how the drainage is provided is as an extra enhance the reliability. Of course, the quality of the construction, the quality is poor, the entire system gets very bad reliability. So how variability, I was telling you, how it gets variable and how it can be predicted for the payment life. The temperature is a variation like this. The temperatures get variation. See, and as the temperature variation, as for stiffness, as you know, as for stiffness is a function of the temperature. Therefore, as for stiffness is also varies. Okay, and another one is this stiffness is a function of strain. Therefore, to that extent, the strain also varies. Okay, this is as far as the asphalt is considered. See, for example, you have a soil strength. Instead of temperature, you can make the moisture content. Okay, as the moisture content varies, the soil stiffness is a function of moisture content. Therefore, to that extent, the stiffness of the soil gets changed. To that extent, and the strain gets changed. Okay, payment stiffness. Therefore, this varies with different phenomena. This varies with different factors. Therefore, we cannot say a single point estimate. Therefore, there is a variation of the strain. Okay, the strain has a own distribution. Therefore, as the strain is not a single point strain that you find out from the your conventional deterministic design, you will have a what do you call variation, you have a distribution of the strain. Okay, so this distribution of strain corresponds to the payment life, which has a distribution. Therefore, payment life will have a minimum value and also a maximum value, C, and will have a mean value. Therefore, the pavement life can be expressed as a reliability level. Therefore, if you want to find out a mean value, this is called your 50% reliability level. Okay. Therefore, you have to enhance to the 90% reliability level. It is possible. Therefore, you might have seen your IRC 37 and all. This is called as your 90% reliability level. Okay, good. Fine. The pavement design, as you know pretty well, how pavement design varies. The pavement design varies with the traffic loading, which in turn got from the contact pressure, wheel load, axle configuration, loading time, repetition of loads. Okay. Then material characterization, you know how materials there. Okay, all types of materials. What is material for the top bituminous materials for a wearing coat, then to the binder course, and you know from the base course and also for sub base course you have a different materials and your own subgrade. Okay, if it is a made up circuit, okay, and what is the soil below subgrade, that also matters. Therefore, the entire thing has its own variations. Okay, that material characterization you have to make it, and with respect to its variation, with respect to its uncertainty characteristics. Okay, then environmental factors, not only this. Okay, these material characteristics varies with the different values. Okay, but with temperature also this varies with the precipitation. Okay, these things also matters. Okay, these also with the moisture content also it varies. Similarly, you have analysis model. The model have different uncertainties incorporated. Okay, if you have an empirical model, it is having a it will give you a point solution, but it also varies, and you know how much reliable each model is, and you are trying to go towards the mechanistic model, and the immediate step is your mechanistic empirical model. That is what is the present time. Okay, now the time is mechanistic empirical. So what is mechanistic empirical? Okay, mechanistic empirical means it has a two part. Okay, and it is an advanced power empirical. Therefore, what you have made is in an empirical system you are attaching a mechanistic part. Therefore, what is a mechanistic component? We try to find out stresses and strains from your engineering mechanics or your strength of material or your FEM concepts. Okay, find your from your mechanics part you find out what is the stresses and strains from the pavement composition you made it. Okay, for a typical design load, okay, that is your mechanistic part. Okay, the empirical part is how these stresses and strains, okay, how they are related to the failure criteria. For example, if your failure criteria is rutting, that is your permanent deformation. Okay, and how much is the permanent deformation is accepted. Okay, that is related to your stresses and strains, and you find out this is the number of repetitions that can be made. And similarly for the fatigue cracking. Okay, these are the two present failure modes we have, and still other present modes like top down cracking has also been incorporated, and we'll see how the research goes. At present in the Indian scenario we have two components, and they have the same way the top down cracking is also dealt. It is a mechanistic empirical concept. So you incorporate your climate into your material characteristics, then traffic. Okay, and this material characteristics is put into the structure. Okay, and you have structural response with the mechanistic mechanics part of it. Okay, you use some FEM tool or layered elastic analysis formula. Okay, in that way you will find out its response, stresses and strain. Okay, you know the distresses. Okay, this distress is related to this damage, and this damage is related to response. Therefore, distress, damage, and response are connected in series, and these things are interconnected. Therefore, this is your mechanistic empirical part. Similarly, in the overlay design, okay, as you know pretty well, your overlay design in your IRC 81, okay, it deals with the overlay design and based on the experiments which have been conducted over a period of time. Okay, so therefore it has come, the IRC 81 has come. That is based on the Benkel beam deflection. Okay, that is, if you go through that, you will find out how that can be made, but it is based primarily on the empirical road. But in IRC 115-2015, Okay, there is a structural evaluation procedure that can be made from FWD. Okay, FWD is nothing but falling weight deflectometer. From the falling weight deflectometer, you can calculate the what you can find out what is the properties of the existing properties of the soil, existing of the pavement. Okay, or the pavement composition from the FWD values. So these values you can catch up and you can find out what is the different properties of the material. Then you go forward approach and what is the present strength and what is the additions you can make it, and you can find out the strengthening part of it. Therefore, that is the mechanistic empirical part of the overlay design. Previously, see, CBR methods have been used, and some reliability principles have been incorporated, but that not all went before 2000. You can see that these are based on the CBR methods, but later little concepts been made because not to use the CBR methods. They are trying to use the resilient modulus. Therefore, all these have been outdated. We can use it for resilient modulus. Of course, to find the resilient properties of the soil, it becomes very difficult. Therefore, there are correlations available from the CBR and to the resilient properties of the soil, and it has been converted. But in the earlier designs of FASTO, and they have used the reliability concept as a lower level concepts in 1993. See how they have used this. I will just show how it will use here. This is how they have used. They have the two equations. Log W18 is your number of equivalent standard axle loads. Okay, that can be calculated from the empirical equations on the right side. So you just long equations and primarily varies with structural number. Sn is a structural number, and MR, that is subgrade resilient modulus. You have a subgrade resilient modulus, and delta PSI. Delta PSI is nothing but what is the change in your serviceability. Okay, change in serviceability. So therefore, originally you have a serviceability level, say for example 4 point something, and what will be the loss of serviceability up to maybe 2.5 level, you can get it. Therefore, some 2.5 times or 4 levels delta PSI can be put. Therefore, accordingly, you can find out what is the W18. Okay, W18 is the number of 18 kips, our equivalent to our standard loads. That is what they put. That is equivalent standard axle loads. You can calculate it. But you can see that there are two variables here. In addition to that, ZR and S0. Okay, ZR and S0. You can find out. I want to see some pointer options here. Laser pointer. See, you found out here there are two things: ZR and S0. ZR is nothing but your standard normal variant. That is nothing but your reliability level. Now, what reliability you want, you can fix it here. Okay, that is the reliability level. Similarly, S0 is the overall standard deviation for the uncertainty. So it primarily depends upon this S0. It depends upon what is it? Traffic and your material characteristics. Okay, traffic and material characteristics. That is what it provides. That they have introduced a small values of reliabilities there, not totally. Okay, here ZR and S0. They have, as in other words, they put as a safety margin. Okay, they have incorporated in terms of a safety margin ZR and S0 here also. Therefore, even for rigid pavement also they have made like this. So these are the two equations they are available from your 1993 ASHTO code. So this is how it comes, the functional classification. So they have a functional classification for different roads. Okay, reliability level they have fixed. For if it is urban roads, if it is freeways, it can be between 85 to 99.9. Principal arterial 80 and 99. Collector 90 to 95. For a local stick between 50 and 80. Similarly for rural roads between 80 to 99.9, like this. Okay, for it all depends upon whether it is a urban or at a rural scenario. You can see that at a rural scenario you have a reduced reliability, and for urban scenario you require a higher reliability to enhance the safety. So ZR for 5% exceedance level, you can find out ZR as minus 1.645. So for other reliability levels 50 to 92, so 50 means 0, 1.4, 0 only standard deviate because it is a mean value. So it is 60 means this much. So accordingly, you have a higher reliability range. Therefore, ZR can be said as a normal deviate, but in later cases we can set as a reliability index. This can be said as a normal deviate, but later we found out as a whole we can put as a reliability index. So if it is reliability index is 3.75, you can see that is 99.9. For example, if you want to have a 99.9, you require a reliability index of more than 3. Okay, that's what it means. And you have another factor is called as standard deviation. Yes, not. It all depends on traffic and the performance uncertainty, and it varies from 0.35 to 0.5. You can take for design purpose 0.45. They have taken directly as 0.45. The research is available. You can put anywhere value because they do not know where to put. Okay, there is a great chance for research. So in our IRC case, you have equation for two equations, fatigue and rutting. So for 90% reliability, you have 0.5161. See here 0.5161. You have a equation. It all depends upon your tensile strain and your resilient modulus of the bituminous layer. Okay, this is what you have. For example, instead of 0.5161, 1.6064 can be made. So a higher reliability, 80% reliability, this value can be enhanced to 1.6064. This is what I would like to say. Therefore, for a lower reliability, you will have NF will be more obvious. Similarly for rutting. So for example, lower reliability is 4.1656. Okay, this is the equations you have in the IRC 37, and rutting is reduced to 1.41, directly reduces for 90% reliability. Therefore, where to use this 90% reliability or 80% reliability? The code gives. Okay, for important for expressway directly, yes, expressways, national highways, state highways, and urban routes. Directly you use 90% reliability. Okay, whenever you have a higher for a 20 MSC or more, your traffic level is 20 MSC or more, then also you go for 90% reliability. Okay, therefore only for a rural type roads, which is not that much important, for a low volume roads, you can say as 80% reliability can be adopted. For other cases, go for a higher reliability of 90%. South African code. Okay, so they also say that they have classified as different roads. Okay, interurban free roads, interurban character roads, rural roads, and lightly trafficked rural roads. They are also lower percentage. Okay, 50% reliability, and they are used called as approximate design reliability. So, if 50% reliability means you can design for mean. Okay, if the mean strengths are more, that's fine. That's what the reliability says. And you should have a 95% reliability for major roads. This is nothing but this major roads is nothing but you can use as NH. Okay, NH as in freeways. So how this approximate reliability is incorporated? So you have material classification, structural analysis, pavement response is there, and you have a transfer function that transfers the response to the pavement life. Okay, in this transfer function, this is incorporated. Reliability is incorporated. Okay, that's what. So you have two different transfer functions for each reliability. That's what I would like to say. So this is the their MEPDG concept for the South African practice. Similarly, in the AST roads, okay, in the AST roads, the motorways you have 95% rate, other access roads is 90%. So that is other roads. Our ODR or village roads, panchayat roads becomes your other roads for equivalent to Indian roads. So other roads is nothing 90% reliabilities. For motor roads is nothing but our expressways and NH. Okay, so 95, and our state highways and urban roads we can go for a 95% reliable. That is what the AST roads practice. Okay, then see how the distribution varies. We want to Bank says that it has a variability from inherent variability. Inherent variability means the structural itself has its own variability. Then you use some model. Okay, model has a variability, and use some statistical data for these models, and that statistical uncertainty is also countermeasured. Therefore, the uncertainty can got from these sources. And as far as the design parameters are concerned, you have a traffic, material, model, and environment. These are also having a particle the distribution. That is, the way uncertainty is there, randomness is there, hence the variance. Therefore, it has a mean and a variance. Therefore, if these things are having a variance, why can't the output? That's what I would say. That we have discussed. Both NF and R as a mean and variance. So, for example, how the distributions would be, and how these researches have been made. Okay, the layer thickness. If it is a bituminous, the coefficient of variance, okay, is coefficient of variation. Its coefficient of variation is 3 to 12%, and you can take as 7%, and the distribution is normal. Okay, therefore, layer thickness is almost a normal distribution, and a overlay is there if it is a normal log normal distribution. This is what the researchers have found out. And the elastic models, the properties of material. Okay, material is, you can say as geometry of the system. You can say the material properties, and these varies with the normal or log normal distribution. Okay, normal or log normal distribution. Bituminous varies with normal or log normal, and the variations, you see higher variations are encountered. See coefficient higher variances, and typically is, you see higher values, 20% is there. And these are CBR base soil has 20% variations, and this also all have them higher. Traffic they cannot predict because it is over the period of time, you know, so it will have a higher variation, and not only it varies, but also you have to find it how it varies over time. Okay, that is what they have not put here, and it can be a normal distribution, log normal distribution, or a Poisson distribution. It varies with time to time, place to place. Therefore, it should be more site specific. Okay. So how fatigue life distributes? See here, the fatigue life distributes for a typical work they have made over simulation. Therefore, 5% is 25 MSA, 95% is 409, mean is 140 MSA. It means if you expect that 95% is often get failed, you can design for 404, you can take as 400 MSA. Okay, if you want to have a lower 5% percentage, that means you allow only 5% failure. It means 25 MSA. Mean is 140. Okay, therefore you can say that what is 95% reliability for this fatigue life is, you can say these are 5% criteria. Therefore, reliability for 95% is 25 MSA. Okay. Similarly, for deformation life, deformation is your rutty life. Okay. Here you see, find out what is mean. It is 97 MSA, and the 95th percentage is 266. Okay, 266 MSA. Whereas for 5% is 19 MSA. Therefore, you expect only 5% failure. It is 19 MSA. You expect 95% failure. Your strength is 266 MSA. Therefore, where is your reliability comes? Therefore, if you want to have a 90%, 95% MSA, you can say this, the deformation life is 19. So, therefore, what is the takeaway? What is the takeaway? Therefore, the system is not a deterministic, number one. Okay, any pavement system or any system for that matter is not a deterministic, number one. Number two, many of them, the system is connected in series, and to enhance the reliability, you have to make the system parallel. Second one. Okay, and how a series system is connected and parallel system is connected is there. Therefore, as there is a variation of the individual component or individual agglomerates, okay, therefore the agglomerated component, okay, individual agglomerated component or the system agglomerated system, the reliability gets reduced because these systems are connected in the series. Therefore, and not only that, each component is varies having a distribution, and the end product also varies with the distribution. Therefore, we have to find out where we stand. We have to find out what we like. What we have to stand where, how we are going to design for a particular reliability level. We cannot design for a particular, for a whole, absolutely successful system. Okay, therefore we always fix it. We always fix it with a reliability. Therefore, fix the reliability, stand on it, and you find out, you design accordingly. Or you find out on otherwise, you can also find out what is the present reliability is built in the system. These two topics are entirely research oriented topic, and you can appreciate in the field also. Okay, right? You can ask any doubts. Thank you very much.
Thank you, Dr. SAKTHIVELAN, sir. Audience, you can post your questions as messages, or you can even ask, you can unmute and ask questions. I hope it was quite interesting. You can ask your questions now. Sir is ready to answer.
Oh, I have taken long time. Is it not so?
Right. Now, actually, it is the time is between 10 to 11:15 only. Still 7 minutes or more. You can rightly take the time for questions.
Those who pursue some research works can also take this as a research topic. You can enhance your research by incorporating the reliability concept into it, or a probabilistic concepts.
Good morning, SAKTHIVELAN, sir.
Yes, sir. Good morning. Shaktivel here.
Sir, I wish to know what will be the percentage of MSA with respect to speak, that is 95% MSA, whatever it may be, so that the pavement will be within elastic limit.
Actually, what happens now? See, you have to find out the distribution. You have to find out the distribution, and you find out what is the 5% or what is the 5% strength, and that 5% strength corresponds to 95% of the reliability. So what you have to find out is you have to make either a detailed reliability analysis, or you have to find out the Monte Carlo simulation and find out the distribution over the entire scenario from 1% to 100%, and you keep it what percentage you want. For example, if you want to have a 90% reliability, you find out what is the 10% failure rate, and you will find out the 90% reliability strength.
Thank you, sir.
Thank you. Thank you. And the Monte Carlo simulation, since it is not the part of our approach here, but those who are interested, they can have a separate course on Monte Carlo simulation, and they can come with me.
Sorry, I have one more question.
Yes, sir.
Is there any possibility by reducing the MSA so that the damages to the road can be reduced or make it to zero?
You want to reduce the damage by enhancing the reliability?
No, reducing the MSA.
It all depends upon your traffic level only. So see, what we do is you are given the traffic level and all. Okay, you are given and you want to design it. Therefore, why you want to reduce it? If you want to reduce it, you can reduce the traffic level. But what is required is for the given traffic level, you have to enhance the system. That is what is required. Therefore, for a given traffic level, you enhance the system by using additional. You use the additional reliability. That means additional reliability can be got by additional pavement thickness. Okay, if you want to reduce for a given pavement thickness, if you want to reduce the traffic, okay, but I do not know how you will reduce the traffic level. Okay, that is possible when you make an alternate road system. That is your traffic planning system. That is your traffic planning methods. You can reduce it.
Yes, sir. Understood. Thank you.
Okay.
Thank you, sir.
Yes.
Thank you for lecture, sir. So, participant, do you have any further question? You can just even unmute your mic and you can directly ask question to Dr. Shaktivelan, sir. So, meanwhile, you kindly fill your feedback in the feedback form, which is posted in the chat box.
Thank you very much.
Thank you, sir. Thank you very much, sir. And
Thank
the
you,
next
sir.
session is also be resumed by Dr. Shaktivelan, sir, on the topic of a decision support system for the maintenance management.
Sure.
Sir?
Shobana, 1 second.
Sir?
There's a small change.
Okay, sir.
There's a small change. I'm sorry. My audience, Shaktivelan sir has a conference presentation now. So instead of Shaktivelan sir, the third session expert, Dr. Arivilagan sir, he is going to present now. There's a small change which happened today morning. So I didn't update Shobana. Shobana, I'm sorry. I don't
Okay,
update
okay,
you.
fine, sir.
And you can ask Shivaraj also to post that. Like I think you would have done it. He knows it. Dynamical system-based approach on soil deformation by Dr. Arivalan. Just now I'll call him. I think, sir, whether he's available. Sir, have you come in, sir? I'll check. You inform Shivaraj.
I am here, sir.
Actually,
Yeah,
sir,
sir is there. Yeah.
Good morning, sir.
Good morning, Professor. Welcome you. Shobana,
Yes, sir.
help sir to. Thank you, sir. Thanks. You're showing your face. Yes, sir. Help sir to present his presentation. Like he wants to share his presentation. Just
Yes, sir.
guide it. Yeah, sir. You can. Shobana will help you, sir. Just now.
Yes, sir. Yes, sir.
You can just open your presentation as well as you can go to that. Shobana, please inform
Yeah,
sir.
sir. Sir, can you able to open your PPT, sir?
Yes, madam. I will do that.
Yeah, sir. Because
Yes,
we doesn't make it.
Let's start.
The session is going to start at 11:30, but sir can open his slide and keep it ready. Ask sir, present now. One small icon is there, sir. Present now. Just go and click it, sir. That right side you can see present now. One arrow mark is there. Present. Just click it. You will get your entire
Option
screen.
like
Yeah,
entire
that's
screen.
what. That's
Yeah,
what.
yeah.
Yes, sir. There you have to click it, sir. Again, like. Yes, sir. It is done. Good. Great, sir. Go to the presentation mode and keep it ready, sir. That's all, sir. Thank you. Shobana,
Yeah, sir.
you have the write up about sir. Brief note.
Yes, sir. I have. I'm just checking, sir.
Yeah, you should
I
have.
will.
I sent you already.
Video presentation. You paste there, la.
Sir, சார் நீங்க ப்ரெசென்ட் பண்ணும்போது உங்களால பார்ட்டிசிபென்ட் ஃபேஸ் பார்க்க முடியாது. ஐ திங்க் ஒன் see that only we can see your face and
Yes, sir.
slide both. Yeah,
Okay,
we
sir.
can see
Okay.
both your face and slides, but you are
Okay.
in Google Meet. When you are presenting, you can see only the slide. I'm sorry for that. There is a setup of the Google Meet, not like Zoom.
Okay, sir. Okay.